One of the most important properties of any material is the dielectric constant. So what is the dielectric constant? Well, imagine we have two charged plates. So we've got positive charge here and negative charge here. And we have a vacuum between them. We know we can draw the electric field lines very simply from positive to negative charge. Now let's imagine that instead of that first situation, imagine we still have two charged plates. And so of course we still have that original electric field, draw like this. But imagine now we're going to put in some inert gas. Let's put in some krypton. Or perhaps we can put in some nitrogen. Doesn't really matter. In any case, we know this electric field is going to push the protons in those gas atoms to the right, and it's going to push the electron clouds to the left. So if we draw in those atoms or molecules of N2, we know that the electron clouds are going to be pushed towards the positive plate. The protons are pushed to the right, so they're distorted. So we'll draw that this way. We'll say that the molecules become polarized because of the field. We've induced a dipole moment by the electric field caused by the two plates. Now if we look at the electric field caused by those dipoles, we can see it is going to the left. So the net effect of this is to decrease the field strength. So the electric field in this example in the center is going to be less than it would be if we just had a vacuum between the plates. In the third example, we still have two charged plates, electric field going from left to right. But this time, let's go ahead and put in something like HCl gas, so dry hydrogen chloride gas. We know hydrogen chloride has a strong dipole, so we'll put that in. And we know that although the dipoles can rotate freely, they're going to tend to line up more with the positive end of the dipole, the H, in this direction, and the negative dipole in that direction. Depending on the strength of the field, they won't be locked into position. They'll be rotating, but the rotation will be biased towards this orientation. If we draw the electric fields for these dipoles, we again get arrows pointing to the left against the original field. So the net effect is that the field between those two plates is much weaker than if we just had a vacuum. And so we'll summarize that the electric field is in this case much, much weaker. The magnitude of that field is much weaker than the original electric field. Here you can see also that the field's weaker than the original field. And we'll just call this E naught over here. Okay, so we can decrease it a little bit just by putting anything in there. Doesn't matter what it is, because regardless of what it is, it will become somewhat polarized. We'll induce dipoles in the material. And we'll reduce it by quite a bit if there's pre-existing permanent dipoles in the material. We can measure this effect, and the ratio by which the field strength is reduced is called the dielectric constant, or the relative permittivity. So we use epsilon sub r to denote dielectric constant. Let's look at some values for dielectric constant. All right, so here we have the dielectric constants for several materials. And we can see that if we have molecules with a permanent dipole moment, we have quite big values for the dielectric constant. And if we have something that's nonpolar, its dielectric constant is not equal to 1. It does actually reduce the E field strength by a factor of roughly 2 because it can be polarized. So it doesn't have a dipole moment, but it can be polarized. What I want to do is focus in on these compounds right here. Notice that their dipole moment is essentially identical because they all have this hydroxyl group, this alcohol group. However, their dielectric constants are quite different. Why is that? Well, if we look at this, we can see that the smaller molecule has a bigger dielectric constant, and this one has an intermediate one, and then the butanol has the smallest of the three. And so this tells us that the dielectric constant is not just a function of dipole moment, it's a function of dipole moment density. So in other words, if we look at butanol, we have the same dipole moment, but then we have all this sort of wasted space in the molecule that doesn't contribute anything. And so this makes sense if you think about it. If you had not butanol, but maybe an alkyl chain of thousands of carbons, you can see you'd have hardly any dipole moment in your liquid. So anyway, the take-home message is that dielectric constant is primarily a function of dipole moment density of a molecule. And so when we say that, for instance, that water is more polar than butanol, we're not really talking about dipole moment. We're really talking about dielectric constant.